How do you design IIR filters in digital signal processing? If you are curious about how to design infinite impulse response filters in digital signal processing, you are in the right place. IIR filters are essential tools in signal processing and control systems. They are unique because their output depends on both current and past input values, as well as past output values. This recursive nature allows them to have an impulse response that lasts indefinitely. Let's break down the design process step by step. First, you need to define the filter specifications. This means determining the frequency response characteristics you want. Key specifications include the passband edge, stopband edge, allowable ripple, and attenuation levels. Additionally, you must specify the sampling frequency of your digital system. Next, choose an analog prototype filter that meets your specifications in the continuous time domain. Common choices are Butterworth filters, which have a flat magnitude response, Chebyshev filters that allow ripple in either the passband or stopband, elliptic filters that have ripples in both, and Bessel filters that provide a linear phase response. Typically, you start with a low-pass filter and apply transformations for other types. Once you have your prototype, calculate the poles and zeros of the analog filter based on your chosen specifications. This step involves using established formulas and tables specific to each filter class. Now, it's time to convert your analog filter into a digital IIR filter. You can use various transformation methods. The most common is the bilinear transform, which maps the analog S-plane to the digital Z-plane. This method preserves stability and avoids aliasing by warping the frequency axis. Another method is impulse invariance, which samples the impulse response of the analog filter to create the digital version. However, be cautious, as this can introduce aliasing if high-frequency components are present. After transforming the filter, you will need to calculate the filter coefficients. These coefficients define the difference equation of the IIR filter. The general form of this equation is where the output at a given time is a function of current and past input values and past output values. Next, analyze and verify your filter. Evaluate its frequency response to ensure it meets the original specifications. Check the stability by confirming that all poles lie inside the unit circle in the Z-plane. Assess the phase response and group delay as needed for your application. Finally, consider implementation aspects. IIR filters are efficient because they achieve sharp frequency responses with a lower order compared to finite impulse response filters. However, they have nonlinear phase characteristics that can affect signal phase unless compensated. Be mindful of quantization effects and finite word length in digital hardware, as these can lead to limit cycles or instability. Choosing the right filter structure, such as direct from Roman II, cascade, or lattice structures, can help mitigate these issues. In practical applications, IIR filters are widely used in audio signal processing, communication systems for channel equalization, biomedical signal filtering, and control systems where real-time filtering is essential. By following these steps, you can successfully design IIR filters tailored to your specific needs in digital signal processing.